Okay, so in this tutorial we are going to look at methods of charging with the idea that most objects have plenty of charge in it, yet they usually are neutral. So we want to understand what are the mechanisms by which we can take a neutral object that has charges in it and make it charged. There are three such methods. One we've talked about last year and a little bit the other day. The other two the other one we've kind of inferred, we've implied, and the last one is a little bit more abstract. We're going to talk about the processes and we're going to represent them pictorially or modeling them, and you want to be able to draw simple diagrams and the steps that may need to be taken for some of the problems. So pay close attention to the diagrams as well as to the actual descriptions. Okay, so again, the overall question is how does one charge an electrically neutral object? All right, the first one is what we call charge by friction. All right, that really just means rub two things together. And actually, we've got to be more careful than that. It's not just any old two materials. Generally, you have to rub two insulators together. All right, like fur and rubber material, glass and silk, wood and paper, paper and plastic, etc. Okay, what it does not work for metals. Okay, so you cannot rub a metal and really charge it. So just to make that clear. So I'm going to show you an example here with the balloon and the head of Bart Simpson here. So suppose most of us have rubbed the balloon against our hair and we know that the balloon becomes charged. So let's assume that it becomes negatively charged. Since the balloon is made of a rubber material, it's an insulator. And a key thing you want about insulator is charges are not really free to move around its surface. So if this part was rubbed against a head, okay, the charges are going to stay there. And I'm going to designate this charge by putting 3 negatives, meaning that there are 3 more negatives than there are positives. Remember, that balloon has a bunch of positive negatives in it. They're neutral, so we're not going to draw them. We're just going to draw the excess there. So where do those negatives come from? Well, we didn't create them from nothing, so they had to come from somewhere. Well, they came from the person that was rubbed against. So if 3 negatives left the head there, that means its net charge is 3 positive. And again, I'll draw the positives on that side of the head because the hair is generally not very conductive, so they have to stay where they are. Okay, so that's what that note is saying. I've drawn 3 positives to show a general conservation of charge. If one object became a charge of -3, I'm not going to say 3 coulombs, I'm just going to say -3, then the other object must be a positive charge. So what we say there is the amount of charge gained by one equals the amount of lost by the other. Okay, it's nothing more than conservation of charge. And in terms of describing an object, if it's negatively charged, we say it has an excess of electrons. Okay, so above and beyond the amount that is normally found in terms of equal numbers of positive and negatives. So if I have a neutral object, I might have 50 positives and 50 negatives. If I say something's -3, that means I have 3 above and beyond that. Positively charged, the temptation is to say there's an excess of positives, but that would be slightly inaccurate because that implies that the positives got transferred. The positives can't get transferred in this process because they're stuck in the nucleus. And in positives and nucleus, the protons, they're not going anywhere. All right, they're held there by a very, very, very strong force. So the way to describe a positively charge is a deficit of electrons. Okay, so his head is positive, not because it gained positives, but because it lost negatives. And that's a really important distinction you want to make when we're talking about any process that positively charges something. And that will come up a little bit. All right, so let's jump to the next one, which is so common that we might even think it's a process. All right, and it's called technically charge by conduction. Sometimes called charge by contact, but I don't like that because some people confuse that with charge by friction. And it's very simple. I have an object right here that's negatively charged. I have a lot of excess negatives on it. I simply touch it to another object. So here's the before part. This is a neutral object right here because even though there's lots of positive negatives, there's no imbalance, so I'm just going to draw it as nothing. Afterwards, so over here, after they touch, what I'm going to see is this remains negative, but less so, and this becomes negative and I'm putting 5 on each one, and I'm trying to spread them out throughout. Okay, because the charges don't want to stay localized. They want to spread out as far as possible, and this goes to an important assumption, or what it works best. It works best with conductors. It does work with insulators. If I take an insulator and touch it to something, that other something will take on some of the charge. But it works best with conductors because you have those sea of mobile electrons, which allows the charges to move throughout. Okay, so the important thing we want to see here is I started with a negatively charged object, I touch a neutral object, and now they're both negative. It's just that whatever this one started with, so if I count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then I should have 10 overall and 5 and 5 in each. Okay, so I'm trying to conserve charge in drawing my picture to make it accurate. All right, so why do the charges jump from one body to another? In other words, what makes conduction happen when you touch something? Well, it's because their electrons repel each other and want to get as far away from each other as possible. So if I have all my charges confined to the sphere, okay, they'll go as far apart as they can to the outer surface. When I touch this sphere, it's like a larger room that they can now spread out in. So they will spread out throughout. And a simple analogy is if I were to pack the classroom with 500 people, well, that would be a very uncomfortable and cramped situation. And if we open the door in the back room, then people would naturally go out of that into a much bigger room, and they wouldn't all go in there because they'd be just as cramped. So they go, so they're basically as evenly spread out as possible. So it's ultimately repulsion and the amount of space that they can take up that will determine how much charge goes on a body. So one assumption students make is, will charge flow stop when the same amount of charge is on each? That's what I drew here. And the answer is sometimes. So I'm not going to write sometimes. I want to put yes. But that only happens if each object, in this case the spheres, are the same size. Okay? So again, using my room analogy, if we have 500 people packed in this room and I open the door to a small closet, maybe 1 or 2 people will go in there. It's certainly not going to be half and half. So when we're talking about charge distribution from conduction, we've got to make sure it's clear what size the objects are touching. And that's really what then grounding is about. So let's say I become charged and I want to get rid of my charge. Well, I don't want to touch something smaller than me because I want to get rid of a small fraction of my charge. Instead, if I want to get rid of essentially all my charge, I want to touch something that's much, much bigger than me. Something that those charges can really spread out on. And generally, that's the Earth or anything connected to the Earth. So the Earth is essentially, from a charge standpoint, infinite in size. So that's a poor infinity sign. Okay, so it essentially accepts all the charge from the smaller body. All right, we'll show some demos of that later in class. So let's do some simple problems that involve conduction. We've done some of these before. This is just the formalization of it. So I've got 3 identical spheres. Let's just call them A, B, and C with respective charges. I'm not worried about whether they're coulombs or elementary charges. It doesn't really matter here. Okay, so first question, what's the overall charge? Well, that's easy. Add them all up. So -3, 6, and 15 gives us +18. All right, so we have 18 units of charge distributed through 3 spheres that aren't touching. Now they're brought in contact. Okay, how much charge will be on each? So I'll just draw a little line here that would indicate contact. And now they act as one big body. So if they're one big body, they're going to spread out and take up get as far away from each other as possible. So we don't expect the charge distribution to stay the same. We have to have a total of 18. If they're all the same charge, it would make sense that each one is now +6. Okay, so if I were to draw these spheres again after we've touched them and taken away, I would have +6, +6, +6. So now we can ask, what was the charge flow, or what was the charge flow for the -3 sphere? All right, so what I'm talking about here is this A started as -3 and it became +6. So how did that physically happen? Well, there's 2 ways we could answer that. It became much more positive, so the common sense would say we just added a bunch of positives. But if you recall our earlier discussion, positives aren't allowed to move in any of these processes, so it has to always be a flow of negatives. So in order for -3 to become more positive, it wants to lose negatives. All right, so we could say that if we do the math, -3 minus what would give us +6, right? -3 minus x gives us +6. Well, that's not too hard to figure out. That's going to be 9, -9. So we can say 9 negatives, or 9 electrons, flowed out. Maybe I shouldn't say 9 electrons. That assumes our units are elementary charges, but 9 negatives flowed out, and that would be an explanation. If for the 15 to the 6, then we can say 9 negatives flowed into the 15, and nothing really seemed to happen with the +6. Okay, so again, positives aren't allowed to flow, so if something becomes more positive, it's not because it gained positives, it's because it lost negatives. All right, so that's the first two. Those are pretty straightforward. The next step in how we can charge things is a little bit more subtle. So I'm going to give two examples, and then I'll stop, and then we'll do the rest in class tomorrow, something that's easier for me to show. So the third way that you can charge something, which is more complicated, is charge by induction. Okay? And what we want to understand about this is no contact is ever made between two spheres, one being charged and the other one being neutral. That's conduction. So if I take a charged object and touch it to a neutral object, this guy will become positive. Don't write this in now because that's all I want to show. So there's conduction reviewed again. Why did this become positive? Because negatives flowed out of it into the other one. So how does induction work? Well, in order to explain it, I'm going to do a preliminary step first and talk about something called polarization. Okay, and polarization is the idea that a charged body can influence charges in another body without touching them. And that's really just Coulomb attraction or Coulomb repulsion. So let's take this situation here. I have a positively charged body A, and I bring it up to a neutral body B. Okay, now B has lots of charges in it, but it's overall neutral. So if I bring up a positive here, it's going to influence the charges in there, especially if they're conductors. And it would make sense that the positives here are going to attract the negatives of this side. Let me just draw 4, leaving the right side positive. The positives didn't necessarily migrate over there. They were just stayed where they were while the negatives migrated to the left. So the overall charge of B is still 0, but it's now polarized. And if we take A away, move it far away, what's going to happen here? Well, they don't feel the influence of A anymore, so it's going to go back to their original state, which I'll now draw as just positive and negatives next to each other. Or you can just leave it blank. Okay, so that's simple polarization. And I can show you that with an electroscope tomorrow. Now that we can use this process very cleverly to actually make something charged. In this case right here, we never charged it. We just influenced the charges, but they went back to their normal state once we took away that influence. But if we do some intermediary steps, we can get an overall charge. So I'll end with this last one. This is induction by separation. I really can't demonstrate it in class, but it's easy to visualize. So again, let's say I have a negatively charged influence. So I'll make A negative. And I bring before it not one sphere, but two spheres, B and C, that are touching. Okay, so B and C act as one big sphere. So what happens when I bring A near it is, again, we're going to influence the charges in B and C. We're going to polarize it. So think to yourself real quickly, what's going to happen in terms of the charge distribution? All right, hopefully you realize the negatives are going to be pushed away, leaving this side positive. All right, so right now this is a state of polarization. Now, before I take A away, what I can do is separate B and C. So if I separate B and C, then the negatives and positives are trapped within their respective spheres, and I've charged them. And the beauty is, I never had to touch A to B or C to induce a charge on either one. Okay, so that's one quick example of induction. And the nice thing about this is, this did not lose any charge. I can take this to another set and induce charge on them again, and I can do it again, and I can do it again indefinitely. So very, very different than conduction, where if I touch this to something, it loses half its charge, then loses another half, so on and so forth. Okay, so that concludes the introduction of methods of charging. I'll do some demos tomorrow.